All right, looks like it is time to get started. So welcome everyone in the room and watching on Zoom and YouTube to our first of two press conferences today. It's Wednesday, January 11th at 10:15 a.m. Pacific here in beautiful Seattle, Washington at the 241st meeting of the American Astronomical Society. I'll be your host today. My name is Kerry Hensley. I'm the Deputy AAS Press Officer, and I'm being assisted today by our AAS Media Fellow, Ben Cassess, as well as Amy Oliver from the NRAO, who has graciously agreed to help run a microphone around during the Q&A. So there will be several press releases distributed associated with today's presentations, and the press kit is now up to date with all of the briefing videos and slides from the previous days. So a brief overview of how our press conferences work. We're going to hear from each of our speakers in the order you see them sitting here, and then we'll have time for Q&A for all of our speakers together. We won't pause for Q&A in between our speakers. For our offsite journalists, reminder that you're going to use that Q&A feature on Zoom to queue up your questions. And yeah, we're off to the races. So this morning, the topic of our press conference is building systems in our local universe. And each of our presenters is going to have a different perspective on what it means to be building systems. Our first speaker will be joining us virtually. That's Kellen Lawson of the NASA Goddard Space Flight Center, speaking on JWST images of a young planet-hosting debris disk system. Next will be Lustig-Yaeger and Erin May, both of the Johns Hopkins University Applied Physics Laboratory. Had to take a breath before I said that. And they will be speaking on a nearby Earth-sized exoplanet confirmed with JWST transmission spectra. Next up is Margaret Meixner from the University Space Research Association, speaking on more JWST results, early imaging results of a young star formation in NGC 346. Following that presentation is Ümit Kavak from the University Space Research Association as well, speaking on protostellar feedback in massive star-forming regions. And our final speaker is Theo O'Neill from the University of Virginia, giving us a perspective on a 3D map of the local bubble's magnetic field. So with that, I'm going to ask Kellen to go ahead and share presentation slides.
Okie doke. Hide that. Oop, there we go. How's that?
That looks, okay, I'm not gonna mess with that. That looks great. Okay. Whenever you're ready.
Okay, great. Thank you so much. So today I'll be sharing results from JWST observations of a particularly interesting system. So while I've been given the privilege of sharing these results, I want to highlight that this work was possible only because of the contributions and support of the entire GTO 1184 team, whose names you'll see on my concluding slide. So the majority of known exoplanets have been discovered using so-called indirect detection techniques, such as the transit method used by the TESS and Kepler missions. So though small in number, the planets discovered via imaging, shown in green here, fill an otherwise vacant corner in this plot of planet semi-major axis first mass for known exoplanets, corresponding to the planets with the widest orbits and highest masses. So direct imaging of planets is made challenging by the high contrast between the bright diffracted starlight of the parent star and the faint light from planets. JWST eases this challenge by providing a stable observing platform to minimize the diffraction of starlight and by observing in infrared wavelengths where planets tend to be brighter relative to their host star. Today we'll be looking at results from the GTO 1184 program. So this program uses JWST's NIRCam instrument to search for planets, targeting 9 nearby young red dwarf stars. So since red dwarfs are fainter, this again helps to make the relative brightness of any planets more favorable. While prior imaging surveys have generally been limited to planets more massive than the outer planets of our own solar system, GTO 1184 is designed to probe masses below even the mass of Saturn, roughly 0.3 Jupiter masses in this largely vacant region of this diagram. So the target we'll be looking at today is Ümit, which is a 23 or so million year old red dwarf star at a distance of only 32 light years. Ümit is well known for its fantastic nearly edge-on debris disk, which you can see in this Hubble image in the upper right. A debris disk is a disk of dust around a star that results from continuous collisions of small bodies called planetesimals. So in this image, you can also see the signature of a coronagraph, which is used in direct imaging to block the intense central light from the star in order to see details closer in, but at the cost of obscuring anything directly underneath the coronagraph. And then within AU mixed disk, observations have uncovered numerous fast-moving clumps of dust, which might be produced by a yet unseen companion orbiting within and interacting with the disk. So one of these clumps is highlighted in these images, where you can see its motion over a span of 6 years here. And finally, AU-MIC is known to host two planets on very small orbits discovered by TESS using the transit method. And so combined, these factors make AU-MIC a particularly compelling target for further study. And so we targeted AU-MIC with JWST's NIRCam as part of the GTO 1184 program. We conducted observations at 2 infrared wavelengths, 3.5 and 4.4 microns, to help assess any planet candidates we might uncover and to allow some analysis of the disk itself as well. And so we're happy to report that we detect the disk with high significance at both of these wavelengths. So on the top here, you can see the image at 3.5 microns with the 4.4 micron image on the bottom. And so while this disk is well observed at shorter wavelengths, these images from JWST mark the first time the disk has been detected at these wavelengths. And so analysis of the disk itself is ongoing, but what we can say is that we see a definitive blue disk color. And so when we say a blue disk color, what we mean is that the disk appears brighter at the shorter wavelength. This is indicative that the disk is made up of particularly small dust grains, which is generally consistent with studies of the disk at shorter wavelengths. And so in the search for planets in these data, here's what we can say. So if you couldn't guess by the framing, we don't see anything that we believe is a planet at this point. However, by measuring the sensitivity of these data, we can determine the planets we would have seen had they been present to help determine what might still be hidden. So to determine planet detection rates, there's a few factors we consider. So first, as we get closer to the star in our images, the noise level tends to increase. And as we get very close to the star, we also begin to lose some of the planet's light to the coronagraph. So overall, this means that planets are harder to detect when closer to the star from our perspective. Additionally, we have to consider how the planets orbit. And so in this case, we know that the system is highly inclined thanks to the nearly edge-on debris disk. So since planets are harder to detect when closer to the star, a given planet will be harder to detect at some parts of its orbit than at others. And then the final piece of the puzzle is that in the infrared, the brightness of an object is related to its heat. And since more massive planets tend to be hotter, by knowing the faintest planet we can detect, we also know the least massive planet we can detect. And so keeping these factors in mind, we can estimate the average chance we would detect a planet of a particular orbital radius and mass. And so here's a map of our detection rates for the 4 micron data, where the X and Y axes are orbital radius and mass, shown in Jupiter masses on the left and Earth masses on the right. And the color indicates the detection probability. So the contour lines here show the thresholds for 90%, 80%, and 50% detection probabilities. So in this figure, I'd like to highlight a few important details. So first, this region in red here is where the object hypothesized to be ejecting the clumps of dust is expected to lie. And so by combining these detection rates with prior analysis, these data will help to better understand what is actually driving these phenomenon, or this phenomenon. So additionally, you may have noticed that we're quite sensitive to solar system mass objects. However, I'd like to point out that we are not only sensitive to solar system masses, but we're actually sensitive to solar system masses at solar system scales. So for example, a planet with Jupiter's mass and orbital radius would have an 80% chance of detection. A Saturn analog would have a 75% chance of detection, and a Neptune analog would have a 60% chance of detection. And so the confluence of JWST sensitivity, the favorable observing wavelengths, and our decision to target faint red dwarfs has provided access not just to new types of exoplanets, but to exoplanets much more like the outer planets of our own solar system. And so with that, I will leave up some summary and conclusions. Thank you so much for your time.
Just gonna get things set for you real quick.
Well, good morning, everyone. Like I said, or like I was introduced, my name is Jacob Lustig-Yaeger, and I'm excited to be joined here by my colleague Erin May from the Johns Hopkins Applied Physics Lab to present our initial results from our large JWST program to search for the atmospheres of rocky exoplanets with JWST. So over the next few years and ultimately decades, the search for life on exoplanets will fundamentally rely on the detailed characterization of exoplanet atmospheres. And the first step on this journey is to simply detect the presence of Earth-sized exoplanet atmospheres. And while this capability has been predicted as possible for JWST, it's only possible for rocky Earth-sized planets transiting the very smallest of stars, where the contrast ratio is very favorable for Earth-sized planets detection. However, these rocky planets orbit so close to their stars that it puts them in a dangerous position to atmospheric escape processes and raises the question of whether this type of planet can actually host atmospheres that last for billions of years and can be detected. So I'm excited to present our first results of our program looking to answer this question of the presence of rocky planets on Earth-sized exoplanets, and our first observations of the system LHS 475b. Sorry for the string of letters and numbers as usual for exoplanets. So we used JWST's near-infrared spectrograph G395H instrument to observe two transits of this planet in front of its star as a function of time. So here is our data from our first transit in August 31st, 2022, and we observed a second transit 4 days later on September 4th. And the observations are extremely consistent with one another, so we'll just focus here on the first visit. And as you can see, we measured the relative brightness of the star-planet system as a function of time over about 3 hours. And you can see that the star maintained a relatively constant brightness over time until the planet passed in front during transit and blocked about 0.1% of the star's light over the course of about 40 minutes. And prior to these observations, this system was actually called TOI 910.01. It was a planet candidate that had been identified by NASA's TESS spacecraft, but had not been confirmed. And so by fitting our transit model to these observations and ruling out various false positive scenarios that could lead to a planet, these pristine data helped to validate and confirm the discovery of this Earth-sized exoplanet. And moreover, the depth of the transit, the amount of light blocked, gives us a measure of the planet's radius, which turns out to be almost exactly the same as that of the Earth. It's 99% Earth's diameter, plus or minus about 0.5%. And so it's really exciting to get this clean of data on Earth-sized planets. And although this planet shares the same radius as Earth, that's likely the only similarity it has with Earth because it is about a couple hundred degrees warmer than the Earth. So our ultimate goal here was to search for the atmosphere of this planet using the technique of transmission spectroscopy, where now we look at the amount of light blocked by the planet as a function of wavelength of light, where we're looking for increases in the size of the planet due to molecular absorption features in the atmosphere that cause the planet to appear larger at specific wavelengths where molecules are known to absorb light. And so our observations are shown here in white, combined from our two visits into one transmission spectrum. And you can see here that we see a very constant planet radius or amount of light blocked over the near-infrared wavelengths that we investigated. So to understand the sensitivity to atmospheres and the types of atmospheres that this is consistent with, we rely on models to piece together what this atmosphere of this planet could be like. And the first set of models we're going to look at here are hydrogen-dominated atmospheres that are similar to those of Jupiter, Saturn, Uranus, and Neptune in the solar system, where they're similar to the composition of the sun, except enhanced by, in this case, 10 and 100 times heavy elements relative to the sun. And so these type of atmospheres produce very large spectral features that are very inconsistent with our observations. So we can rule these out at high confidence. When it comes to more terrestrial type atmospheres, it becomes a little bit more tricky to disentangle between various atmospheric scenarios. Here we're looking at a pure methane atmospheric model that is weakly disfavored by our data because of the absorption of methane at 3.3 microns, where our measurements are most precise. However, a carbon dioxide atmosphere is more consistent with our transmission spectrum because carbon dioxide produces relatively small spectral features that are consistent with what we're seeing. However, a flat featureless spectrum provides an excellent fit to the observations as well, and this is what we would expect for a planet that does not possess an atmosphere. So, sort of to close things out, this planet very well could be an airless body that has lost any atmosphere that it once had, but it also might possess a compact atmosphere that we are not sensitive to, that could be composed of carbon dioxide, could be a thin atmosphere that would produce very small spectroscopic features, or it could be a thick atmosphere composed of carbon dioxide like Venus that has a high altitude cloud that would also produce a very flat transmission spectrum. But ultimately, to disentangle these two possibilities will require further observation with JWST. And fortunately, we have an additional transit scheduled within this program for this summer. So we're excited to provide an update on this system at that time. To close things out, I'll put up my conclusions and just make this last point that even though we don't detect an atmosphere in this case, our measurements meet the sensitivity requirements to be able to detect the atmospheres of Earth-sized planets. So it's a really exciting time to use JWST, and I think this shows great promise for many exciting years of rocky exoplanet science to come. And I think we're just starting to scratch the surface of what is possible with JWST. Thank you.
So the prior speakers talked about exoplanets and finding them. I'm going to talk about basically, can you do you have the building materials for exoplanets at low metallicity? So I'm going to discuss our recently submitted paper on early imaging results from JWST NIRCam on this young star formation region in NGC 346. On the right, I'm doing this on behalf of this whole GTO team, and the paper is led by Libby Jones. So what is NGC 346? NGC 346 is in the Small Magellanic Cloud, which is a nearby galaxy to the Milky Way. It is the brightest, most massive star formation region in the Small Magellanic Cloud. And what interests us in it is that it's at low metallicity. So its metallicity is about 0.2 solar metallicity. And we're investigating star formation at low metallicity. And we're looking at two different phases of star formation at low metallicity. One are young stellar objects, and these are embedded forming stars, and pre-main sequence stars, which are more optically visible forming stars. So they're at a more evolved stage. Now, Spitzer studies revealed about 87 massive young stellar objects, so more than 8 solar masses, and 33 of them had follow-up for spectroscopic confirmed. So we know we're seeing YSOs. But what about the low mass YSOs? What about the ones that are forming planets like the talks you just talked about, solar mass stars? Now, Hubble found low mass pre-main sequence stars, but it wasn't sensitive to the dust. And so at low metallicity, at the metallicity of the Small Magellanic Cloud, there have been studies shown that the dust content of the interstellar medium starts dropping precipitously. And so it's a very big question. Do low mass young stellar objects have circumstellar dust from which you could make rocky planets? And for that, we've used JWST NIRCam, which is very sensitive. This beautiful image on the right, which is part of the press release, shows the power of James Webb and also the beauty of James Webb. And what you're seeing there are these ribbons of gas and dust in the ISM. And around it, you can, of course, see star clusters and stars. And in this study, we have focused on trying to extract the compact point sources in here. And that's what I'm going to be showing you next. So what we did is we went through and source extracted from this very confused background, the stars, and this is what we found. Now, of course, we're trying to identify low mass young stellar objects. And what we do is use, we have multiple filters with NIRCam, and we use a combination of them, what we are calling a color diagram. On the y-axis here, we're subtracting, and when we're subtracting these filter names, we're really subtracting the magnitudes. And as you go up the scale, they're bluer, and as you go down the scale, it's redder. Actually, I flipped that around. It's redder at the top, bluer at the bottom. Anyway, on the x-axis, again, we have bluer on the left, redder on the right, and so what I want to show you here is we divided this into 4 quadrants. This filter, this narrowband filter of 187, actually also is very sensitive to the Paschen alpha line. So oops, I'll just X that out. Can I hex that?
We'll find out. Yeah.
Okay. All right. We have it here. So some of the things to the right of the blue dashed line have an excess of Paschen alpha emission. And then some of them could also be that they're redder. So as you go up this train here, this kind of, you can see this very clearly. You have this train of sources going up to the right. These are all sources that could be redder, or they can have excess Paschen alpha, or both, right? And on the left, these things are bluer. And then here on this dotted line here, this is sort of separating what I'm going to show you next as sort of main sequence. So stars that we know really don't have excess infrared emission around them. They're, stars, like the sun, and things that don't have much dust around them in excess. So the things in the bottom left corner are what we're going to be calling stars. But the things up and to the right, these are what we're calling young stellar objects. They're more embedded. And then down here, we're calling these pre-main sequence stars. These probably have very or much less embedded nature to them, and they have perhaps this the Paschen alpha excess. So in the next plot, I'm going to show you something that's more similar to. Oops, that didn't advance. Let's see, maybe if I do that. There we go. Okay, identifying again. This is showing the color, what I call a color magnitude diagram, analogous to a Hertzsprung-Russell diagram. So on the left axis, or the y-axis, we're showing the brightness of the object. So at the bottom is fainter, at the top is brighter. And on the x-axis, again, it's the bluer versus redder. So what you see here on the left is this is the main sequence. And then we have all these other things that are basically stars. This is a red giant branch. There's a red clump in black. There's sort of lower mass main sequence. These are all kind of stars. And then to the right, this is just to confirm that the things we identified as pre-main sequence stars, pre-main sequence stars in young stellar objects are indeed at the faintness level we expect. So these are low mass stars. And then they're also redder here as well. So that was another way to confirm of what we found. By the way, this is all posted now online in a paper by Jones et al. So you can get the full scoop there. Let's see, I wonder if we can shrink that down. There we go. Okay, and then the final check is like, where is it spatially located? So remember I talked about in the beginning this beautiful image that has these ribbons of gas, molecular gas and dust that we're seeing with NIRCam. Well, on the left, we have a slightly different representation of that with 3 colors from the different NIRCam filters, showing very explicitly some of these ribbons and the filters that they're shining brightly in. And then on the right, we're just having a grayscale, the 335 medium band image, just to show. And this particular band traces the PAH emission, which kind of traces the surfaces of molecular clouds in the region. And so where you see the gray scale stuff here, this is where we expect there to be molecular gas from which stars form. And there was a paper earlier this week by Laura Lenkick showing the molecular gas is actually correlated with this from ALMA. So again, we're seeing sort of what we expect. The low mass young stellar objects are indeed associated with these clumps of gas, these orange and red things. And then the low mass pre-main sequence stars, which we're showing here in blue, are more scattered. They're optically exposed. They're out there in the star field. And so we feel very confident that we have found these low mass young stellar objects and pre-main sequence stars. And then again, going back to the fact that the young stellar objects, these low mass young stellar objects, have an infrared excess. What's causing that? It's not the surrounding molecular gas. These are, remember, sources we've extracted. They're point sources. And so all these sources have circumstellar dust associated with them. So these low mass young stellar objects have dust. They're dusty. They have, hence, the building blocks from which you could form rocky planetary systems at this low metallicity. Now, the other interesting thing about this low metallicity is the metallicity of the small Magellanic Cloud is comparable to the peak of star formation in the universe. That's when we're basically producing most of the stars in the universe and most of these galaxies. And so this is very interesting because that means that you could potentially be forming planets around a bulk of the stars. All right. Maybe I click there. Okay, and so this is just the summary. So we've found subsolar mass young stellar objects and pre-main sequence stars that we've discovered for the first time with JWST NIRCam observations. And this is due to the tremendous sensitivities. I mean, this is sort of minutes on a field to find these things. That's how powerful James Webb is. And then these initial results increase the young stellar object count that we started with Spitzer by more than a factor of 3. And we've just scratched the surface of this data. We're going to go back and kind of push it down to, brown dwarf almost limits to see what we can find. The important result here is that the near infrared excess that we're finding in these young stellar objects implies there is circumstellar dust emission surrounding these forming low mass stars. And hence you have the building blocks that give the potential for forming rocky planets at low metallicity. Thank you.
Yeah, I think it's coming here. Okay. Hello, everyone. Thanks for coming. And today I'm Ümit Kavak. I'm a postdoctoral researcher at Sofia Science Center and University Space Research Association. And today I'm going to report. I like to share some of our important findings about protostellar feedback in massive star forming regions. And as an astronomer, I'm happy to report that we discovered that this fossil outflow from massive stars breaks the bubble shell in the Orion Nebula, and for that we use Sophia's ionized carbon observations. And because we know that this type of activities in the interstellar medium reduce the number of forming stars and mix up everything and create also new stars. We also found that the expanding shell in the Orion Nebula were broken by these outflows and riddled by the different outflows from different protostars. And our findings basically give the first direct evidence of this outflow activity created holes in the Orion Nebula. And on the right side, you see this our ionized carbon map of the Orion Nebula taken with Sophia Observatory. Why ionized carbon? Why did we use it? Because it's the most dominant cooling line. It traces a broad temperature range from 50 to 300 Kelvin. That corresponds to -372 plus 80 Fahrenheit. It's quite large temperature range. And also it's one of the brightest line that we can observe with Sophia easily. And with Sophia, we collected 2 million ionized carbon spectra, which is on the right side. This is not on an image, but there's also a spectrum in each pixel. And in total, we have 2 million spectra from Sophia observations. And we use Sophia's ionized carbon observations because they also give us information on kinematics. We can basically know how fast structures move and in which direction. And in 2019, Pops et al. Made a revolutionary work, and they published these results. And they found that this bubble, which is on the right side of the slide, this yellow-green colored bubble is mainly driven by the fast stellar wind coming from the stellar cluster within the bubble. And they argued that this bubble will be broken up before a supernova event by this overpressured gas heated up to 10,000 Kelvin, which is 17,000 Fahrenheit inside the bubble. But then we look at the data again, we found that the bubble is not spherical as expected. And we found some additional structures, like if you look at the ionized carbon map on the right side, I highlighted a bubble, but there's this structure somewhere here. This is what we called Orion protrusions. And we thought that this should be an additional mechanism causing this protruding structures at that part of the cloud or bubble. And for that, we made analysis. We used SOFIA data again, and without SOFIA, it wasn't possible to understand the origin of this structure. What we found is that this protrusion were created by outflows ejected by the trapezium cluster, and outflows are just material ejection in the opposite direction, and the star is here, the bright spot. And we found that these outflows also break the bubble, which was supposed to be closed in many studies. And that was our one of the big major findings. And we know that SOFIA provides information kinematics, as I said, and these outflows is moving perpendicular to line of sight. But we can search for the outflows coming towards us using SOFIA's ionized carbon observations. And this is exactly what we did in a follow-up paper. And we basically found 6 outflows interacting with this expanding bubble shell. And we found these structures for the first time, because if you look at this here, this is the bubble itself. But we found these holes here, and this hole big, and if you try to close this aperture, you would need at least 9 million solar-sized suns to fit that gap. And there's this hole, and this is the biggest one. And the outflow causing this hole is moving towards us at 60,000 miles per hour. And we know that the Orion Nebula is hosting almost 30,000 protostars, and each of them has a outflow. It's just randomly like shooting in a region and killing whole structures that you have in the star forming regions. And we believe that this activity is going to make this wheel shell, expanding shell, more like a sieve. And then why these holes are important, because with this heated gas inside the bubble will try to escape through these holes, and the expansion of the bubble will slow down. At the end, this is gonna open, but many studies think that this is going to be through stellar activities, but we found that this is going through this outflow activities that we studied in these 2 papers. Okay, these are my summaries, and we found that these outflows break the Orion bubble nebula, which is, by the way, nearest massive star forming regions. And when we want to test our models about star formation, this is first region that we visited. And we found that these outflows created holes by punching the wheel shell. And we detected these sources with SOFIA, and without SOFIA, it's impossible with the recent technology. And then mainly we can say that this protostellar feedback through outflows limits the future star formation and sets an important phase in the evolution of the galactic interstellar medium. Yeah, that's all. Thank you so much.
This
All right. Hello, everyone. My name is Theo O'Neill. I recently graduated from the University of Virginia, and I'm now working at the Center for Astrophysics, Harvard and Smithsonian, where I did much of the work that I'll be talking about today. So I'll be sharing the first ever three-dimensional map of magnetic fields over a 1,000 light year wide bubble that surrounds our own sun. And so I'll start with our main result. This is a video zooming in on an artist's rendition of the Milky Way into a magnetically mapped bubble into which our sun is in the middle of. This is our best estimate of this quantity, and in this talk today, I'll be giving a summary of how we reached this first ever result. Some of you who attended some of the virtual press conferences last January for the AAS may remember my colleague Catherine Zucker's press conference, where she shared her discovery that the local bubble that I'm talking about today is responsible for the formation of nearly all young stars near our own sun. She found that about 14 million years ago, a series of supernova explosions began to take place. In the process of that combined chain of events, they pushed out most of the dust and gas in the nearby interstellar medium and triggered the formation of young stars in nearby clouds of dust and gas. And our own sun actually happens just by chance to be in the middle of this bubble. We're not particularly lucky or anything. We just think that the interstellar medium is a lot like a block of Swiss cheese. It's full of these sorts of bubbles driven by stellar feedback. So it's pretty expected that we're in the center of one. But since we are in the center of this bubble, we have a really unique opportunity to be able to map its properties in 3 dimensions as a result of our perspective inside of it, in a way that we can't do with more distant bubbles in the interstellar medium. So one of these quantities that we're able to look at for the first time is its magnetic field structure. For a bit of context, magnetic fields play an incredibly important role in regulating the formation of stars on local and galactic scales. These simulations are showing the progression of star formation just under the influence of gravity on the left versus under the influence of gravity, some other factors, and magnetic fields on the right. Magnetic fields regulate the collapse of gas clouds into young stars to yield realistic timescales for star formation. So they play an incredibly important role in our understanding of how galaxies evolve. And since bubbles are so common in the interstellar medium, being able to look at the local bubble's magnetic field is a super important opportunity. When I say that we've made a 3D map, there's some pretty big caveats that come with that. So there's 2 main sources of data that we use for this map. The first is basically geometric projections. So how we convert 2-dimensional to 3-dimensional data as we're looking out into the universe. The second is a series of physical assumptions about how we think magnetic fields and dust and similar factors act. I'll be going through those now very briefly. Our first major assumption is that as from our position in our solar system, we're looking out into the universe along the line of sight. There's a lot of different potential sources of polarization that can come from magnetic fields that we can observe. The first thing we see as we look out is this dusty, magnetic, expanding shell of the local bubble. Beyond that, you can see the more distant interstellar medium in our own Milky Way. Even further beyond that, the intergalactic medium, and even further beyond that, the cosmic microwave background. For this work, we use a dust polarization map released by the Planck collaboration, which is only including the Milky Way foreground and the local bubble itself. Because the interior of the local bubble is a very low density region, we make the assumption, which is a large assumption, but not a terrible one, that the bubble shell is responsible for most of the polarization we see on the plane of the sky as we're looking out along our line of sight. So this plot in the bottom right is showing in blue regions where we think that this assumption is most likely to hold. So our map is probably most accurate outside of the galactic plane itself. Our second assumption we make is that over the last 14 million years, as the bubble has expanded into the ISM, it has swept up magnetic fields that it has encountered to become basically tangent to its surface, as I'm showing here in this animation. So we can combine our 2-dimensional polarization data with 3D geometric models of the local bubble surface to end up with this first 3D map of its magnetic field that I previewed earlier. This is really a visualization challenge more than anything. We explored a lot of different ways of the best methods to explore what might be happening physically in our local neighborhood and to assess physically and statistically different factors that might be at play. If you'd like, you can scan this QR code to explore some interactive figures that we've released along with this paper. This figure in particular is showing the positions of nearby feedback bubbles in the interstellar medium outside of our own local bubble. Since we think these bubbles are so common throughout the ISM, there's probably interactions happening between bubbles. So this map can be hopefully used to probe some of these variations in physics a little further. This figure here is one of my favorites from this study. We're showing projected back into 2 dimensions, the distance from the sun to the surface of the local bubble over the plane of the sky. So yellow regions are places that are closest to us here on Earth. These swirly patterns are showing a 2-dimensional magnetic field, again, projected onto the plane of the sky. And there's also some really interesting correlations that we see between these quantities. This holds up in other surface measurement analyses as well. And it's a really solid indication that our assumptions that we make to go into making this map are fairly not totally off base. So to close out, one really big caveat that I'd like to share is that just like the very first maps of our own planet had some details to be worked out, this map probably also will be able to be refined significantly as we progress. And as the data that we have available and our understanding of physics improves, this map will certainly be refined. But for now, we do have this first 3D map. There's a ton of cool science that we could hope will be able to be done with this publicly available map. A few of those questions, but by no means an exhaustive list. How do these interacting bubbles affect magnetic fields on galactic scales? What can we learn from simulations when trying to apply similar analysis? How can we infer how magnetic feedback bubbles set star formation on overall galaxy scales? And maybe most interestingly, what are the best ways to contextualize and share 3D studies of our Milky Way like this one, of which many have been able to become possible in the last few years? For more on that, I encourage you to check out my advisor, Alyssa Goodman's website, milkyway3d.org, where we have some work ongoing here to share more results like this one. Finally, if you'd like to learn more about this study, please feel free to visit our website. You can play with those interactive figures, watch some other videos, read our preprint, and much more. So thanks for your time, and I look forward to any questions.
All right, excellent. Thank you for those talks. We're going to get started with our Q&A. I'm going to figure out a way to show our virtual presenter. But while I'm doing that, let's go ahead and get started with questions here in the room. And remember to state your name, affiliation, and who your question is for.
Hi, this is Monica Young with Sky and Telescope. My question is for Theo O'Neill. I was wondering if the magnetized bubble or the shape of it can tell us anything. There's obviously a lot of science that you can look at, but I was wondering if you can look back in time and look at the supernova origin of the magnetic bubble and kind of confirm, because I know Catherine Zucker had set out this kind of timeline for how the supernovae might have happened. And can you use the magnetic bubble to confirm that?
Yes, I think it may be possible in the future. That's an area that we're actively looking at and hope to explore further, but there may be able to be insights from this present day map and extrapolating back into time as this interaction of this chain of supernova affected our magnetic interstellar medium.
Hi, this is Ethan Siegel from Start to the Bang. My question is for Jacob Lustig-Yaeger. On the one hand, it's awesome that JWST could, confirm a candidate exoplanet and take these observations during a planetary transit and get good data with the NIRSpec instrument. But seeing no atmosphere or something consistent with no atmosphere makes me wonder, are we stuck in a not sweet spot with JWST where we can get exoatmospheres around worlds that we fully expect won't have atmospheres because they've been stripped away by a low mass, rapidly flaring, non-slow rotating red dwarf star, but not exoatmospheres that might be interesting from a habitability point of view?
So that's a great question. I think it's certainly an opportunity to learn about the physical processes that strip atmospheres from planets and to start to get out towards the habitable zone. So that we're kind of interested in where this dividing line might be between planets with and without atmospheres. And certainly if it turns out that many of these rocky M-dwarf planets don't have atmospheres, it will make it challenging to dive deeper into the habitability and potential for life in these worlds. It could compromise those. It's too early to say, that's for sure. We'll need a lot more observations to get that understanding. But, you know, having only one type of star system, M-dwarfs, to search with JWST, you know, puts us in a position to ask these questions of the M-dwarfs, and it'll be really interesting, I think, to learn about the processes that make these very different stars and their planetary systems different from our own solar system.
Okay, we've got a question up here in the front. And then we have online questions as well after, right? Okay, cool.
Govert Schilling from the freelance from the Netherlands. This is for Margaret Meixner. You said the census of young stellar objects has increased by a factor of 3, but what numbers are we talking about? What absolute numbers? And also I'd like to know more about this star forming region N346, like how large is it? How old is it? How does it compare, for instance, to the Orion Nebula in our own Milky Way?
Wow. Okay. These are all right. Let me start with the first one. So this is just our initial study. So total numbers, we're talking about hundreds of what we found. We expect to go back and probably increase that by at least a factor of 10 or more with more careful processing and probing. But we were so excited to see the dust around these things. We wanted to get that out. Now you're asking about the region itself. The region itself is much, much bigger. Orion's wimpy for a massive star formation region. It just happens to be nearby. Wimpy and for massive star formation. I mean, we have here, you know, Orion has like 4 O stars. Here we have, you know, closer to like 100 O and B stars. And each of like the little knots that if you look in the image, you'll see these little bright illuminated region. One's we're calling like a dragon's head or something like that. And you see lots of little stars in there, you know, maybe something like that's Orion. And that's a small piece of it. So this is a massive star formation region. You have a massive young cluster in there with lots of pre-main sequence stars. And then you have ribbons of dust. And each of these is probably like an Orion, but we have lots of these. You know, and just to extrapolate, like I'm making this analogy between this and sort of the peak epoch of star formation. Well, at that peak epoch of star formation, you probably have thousands of like 3, 4, 6 objects. So, you know, it's kind of a scaled up thing. But one of the wonderful things about the Small Magellanic Light Cloud is you can actually map the whole region pretty efficiently with James Webb, and you can get this whole census. And there's a number of very massive star formation regions that occur. Did I get all your questions? The age of the cluster is what I think it's a few million, 1 million years old for the young O cluster. And of course, the stars that are forming are sort of, you know, pre that age.
Great. Let's hear from Martin, and then let's go to some of our online
Hey,
questions.
Martin Radcliffe of Evanston, Sutherland, and freelance for Margaret as well. Follow really intrigued with the, you know, this low metallicity star forming region that you're talking about, you know, reflects what we might have in the very early universe. And so I'm curious what the molecular or atomic makeup of that dust might be. Is it purely carbon, silicon? How much do you expect? And in order to answer that question, are you thinking of cycle 2 follow-up with NeoSpec or MIRI on James Webb? Which instrument would help answer the abundances?
Yeah, very good questions. The composition of the dust from what we understand from other studies is you have it's sort of similar, but just much lower. I mean, that's done from UV studies of the region, sort of what I call these depletion studies. We are, this region's so interesting. We actually have a comprehensive study. So this is the first of many papers. We have near spec coming out, an early near spec, but we are going to be divulging the whole catalog of this region. And we're going to follow it up with near spec spectroscopy to look particularly for the ice features in this region. And then which to see how is the circumstellar composition different at low metallicity compared to Milky Way. And then to also look at with MIRI. So we have MIRI data as well. And then we have a kind of study that will be coming out sort of in the upcoming months, looking at sort of the Spitzer identified YSOs and studying those in terms of what those turn out to be when you actually can resolve them, because those were kind of point sources for Spitzer. So yes, this is, expect more results to come, and we will learn the composition. And we already had a hint from Spitzer that the composition for the ices is different at low metallicity, but it'd be really good to get the James Webb data parsed out for a lot of the different stars in the region.
Great. Okay. Ben, a question from online.
Sure. Thank you very much. So our first question is from Bill Waller. It's for Kellen. And it was, what sort of orbital periods would planets within the coronagraphic shadow have, and how could they be searched for?
Hey, sure. So thank you for your question. So there's maybe 3 or 4 answers to this question. So if we're talking about a planet whose entire orbit is beneath the coronagraph, that would be a radius of 6 AU or so, or less. And so that would correspond to a period of 20 years or so. However, since we're viewing the system pretty much perfectly edge on, even a planet with a very large orbital radius would pass beneath the coronagraph for some part of its orbit because of our perspective. So that's why all of our detection rates plateau just below 100% or so. And so effectively, there's no planet that we can entirely rule out from one observation. But for larger orbits, the chance of this is, becomes extremely low. So for in this large orbit case, within reason, we could combat this by waiting a few years and reobserving, especially for very bright planets. There's only a few degrees really where we can't detect it at all. And for the less than 6 AU case, so totally beneath the coronagraph, these could actually be detected via transit. Again, this is an edge-on system. It could take a while, right, if it's close to that 20-year threshold of orbital period. But, AU, MIC, B, and C fall into this category. So they're, well under an AU separation, but they were discovered via transit from test data. And so the final sort of caveat here is that for NearCam, the coronagraph isn't actually a sharp boundary. So it's a relatively gentle slope of decreasing throughput. So our sensitivity gets worse as we go deeper beneath it. But we can actually still make detections there. So the entire orbit of a Jupiter analog, for example, falls beneath the coronagraph, but it's simply bright enough that we can still detect it until it's, very, very close to the center of the coronagraph. So I know that's a lot of answers for your one question, but hopefully that answers it for you.
Great, thank you.
Okay. We have another question. This one is for Erin and Jacob from Lisa Grossman, and that is, how thick would LHS 475b's atmosphere have to be detected by JWST?
Yeah, so I think there's a few different ways we could answer that question. One thing Jake highlighted is that the lack of detection here isn't a limit of the planet of JWST itself. It's pointing towards the planet's properties. We haven't reached a noise floor for JWST, so that's where certain systematics can cause us to, no matter how much data you bin together, you can't get any more precise. And we're finding that from our 2 transits alone, any noise floor is about a factor of 2 better than expected, with no sign of 1 yet. So we do think that adding more transits would allow us to get to the atmosphere of these rocky planets. I don't know that I would put a limit on how thick the atmosphere needs to be, because we need to know more about the actual limits of JWST to know what we can detect.
Great. Let's take one more question from online, and then I see Corey has a hand up over here.
Okay, so we have a question from Bill Grunberg from Griffith Observatory for Theo, which was, can we detect other bubbles similar to ours in the Milky Way, and how many do we think the Milky Way might contain?
It's a great question. We can and have detected many such bubbles, so many that I don't actually have a number for you. But even in other galaxies as well, especially with JWST, there have been recent results finding, I believe, hundreds to thousands of bubbles in single galaxies as we're looking at them kind of face on. So it's likely that our own Milky Way is similar.
Hi, Corey Powell, freelance. This is another question for Kellen Lawson. You mentioned that there are 9 M dwarfs in your program, and I know at least some of them are a little bit closer than the system, and you're looking at Fomalhaut C, I believe. Can you just talk a little bit about kind of where you are in that larger observing program, and kind of what the limits are on those other systems? Will you be able to put tighter constraints, or will you be more sensitive to planets in any of those other systems?
Yeah, so maybe I'll go backwards based on my memory of your questions here. So very likely yes, and we're sort of into the preliminary aspects for these other systems. The problem ends up being, well, so AUMIC is pretty much the brightest intrinsically star in our sample. It's M0, and so we have a couple of M5s and M6s as well, where contrast should be more favorable still. So likely every other one of the targets will have better limits in terms of planet detection. The problem ends up being that we're actually running out of models of planets. So we're pretty much at the bottom end of the existing models of low mass planets, for translating their brightness to a mass. So I suspect that we'll go at least as deep as the current models, which is something like I think 10 Earth masses, somewhere around there. 10 to 20 Earth masses. But beyond that, I can't say at this point, simply because the models don't exist yet.
Great. Okay. We probably have. Oh, sorry. Are there further questions in that sub question? Yeah.
I think I got everything.
Yeah. All set. Okay. Cool. We have time for just a couple more questions, and I'm going to see if there are people online first, just because the people in the room can snag our presenters afterwards. Ben, is that anyone else? Just one more. Okay. Great.
All right, this is for, I believe, all of the presenters who talked about exoplanets. Again, from Bill Grunberg of Griffith Observatory. He wants to know if for any of these exoplanet systems, is it possible to determine the approximate age of the host star? And does that help us better understand the planet formation of that system?
I can answer that for us. At least. Other people may have other answers, but in the case of AUMIC, we actually have quite a good age estimate for the system, somewhere around 23 million years. And this is because the star is a member of the Beta Pictoris moving group. So since objects in a moving group all formed around the same time, if we can find the age of one object, then we pretty much know the age for all of them. And I won't get into the nuance of how you do that, but for our analysis, the age is actually super important. So the relationship between the infrared brightness of planets and their mass depends critically on the assumed age of the planet, and so therefore of the system. So since planets cool down over time, right, the age matters very much. So without an age estimate, we'd be much more limited in what we could say about the planets that we should have detected, or even in the case when we do detect a planet, what we can say about that planet in terms of, determining its mass, et cetera.
And for our system, LHS 475b, the age is important in the context of how long an atmosphere would be stable there for really detailed theoretical calculations. In this case, this star is not particularly well studied. Now that it is known to host Earth-sized exoplanet, I imagine a lot more effort will be done to narrow down on the age constraint there. But we do expect it to be sort of like a middle-aged main sequence M dwarf star somewhere in the range of 7 billion years old, plus or minus a few billion years.
Great. Okay, we can have one more question from in the room coming in under the wire before we close the session.
Great, thank you. This is Lori Chu from NASA Ames, and this is for Ümit. And I was just wondering, have you looked at the proper motions of the stars in the region to see how they kind of correspond to some of these outflows that you're seeing?
Oh, thank you so much for the question. Yeah, we try to identify the protostars because they have a proper motion, but we couldn't find a connection between the structure that we found and the stars because for outflows, you need time of like 10⁻⁴ years, 100,000 years. And in this time, one star can even move out of the region, like out of the bubble, because they don't have intersection and they can just go away from the region. And yeah, we just look at that correlation too, but we couldn't find any like a proper relation between source and the protostar, source stars, whatever.
Great. Thank you so much for all the presentations and all the questions. Thank you for joining us here this morning, and especially to the PIOs who helped prepare press releases, as well as our sponsor, the University Space Research Association. We will be back here in this room today at 2:15 p.m. to hear about discoveries in the Milky Way's backyard and in the universe at large. So with that, let's thank our wonderful speakers one more time.